So now consider one more example. So let's say you have a set of number, say positive integer. And we say that it have distinct sums if the following holds. If all sums, so you take some subset S of this K, you consider this, then they are all distinct over all subsets S over here. So there are 2 to the K many subsets S we can take, capital S. And for that we take this summation and they are all distinct. Then we say that this has distinct sums. And let Fn be the largest K such that there exists a set x1 to xk, which is a subset of bracket n, and they have distinct sums. So, what sets have a distinct sum? So, for example, if you take 1 to 2 squared to third, so you take all the power of 2. Then, what do we have? If you choose a set F here, which is a subset of this floor of log n, taking bracket, then, this S, this summation of, let's say this is x1, x2, and so on, this gives us a number which has, if you write in binary expansion, the places where you have 1 is the digit that you have 1 is exactly same as S. So this means that for two different S and S prime, you will get this different number. So this is a set which have a distinct sums. Here we want to find the number which is the largest K, such that you can find the set of size K which has distinct sums. So this shows that we trivially have this Fn is at least as large as 1 plus the floor of log 2n, because this is 2 to the 0, 1, so the size of this is 1 plus floor of log base 2 of n. And Erdish actually offered $300 to prove or disprove that this is essentially best possible. So meaning that Fn is always at most log n plus c for some constant c. So this is one way to make sets with distinct sums, but we don't know whether this is the best way. There is another way which is even better. So Eredish ask is that essentially, this is up to constant. This is near optimal. So this gives us a lower bound, and if you want to show upper bound, one easy way is that when you have say one such optimal set with the largest set with distinct sums, then how many? 2 to the Fn many sums are there, and they must be all distinct. And because each number is at most n, then let's say this k is no, then and the sum that we take there is, you add at most fn many terms which has value at most n. So the order 2 to the fn many sums are at most this number, and they are all distinct. So it's between between 1 and this, and then they are all distinct, and there are this many. So we must have this inequality. And if you solve this, then you actually show that this fn is at most log n plus log n plus big O of 1. So this is an upper bound. And we can actually prove a slightly better upper bound by using second Moore method. That bound is this. So this second term can be, half of this. So if we can completely eliminate it, then we answer the question of Eridich. But instead of completely eliminating it, we can actually eliminate half of that. So how do we want to do it? So we first, obviously we want to use probabilistic method. Let's say we fix a set having distinct sums with the optimal value at k, possibly. K will be fn. And what we will do is let epsilon 1 to epsilon k be the random variable indicating whether we will add xi or not. Which have value 0 or 1 with probability half, so uniform random variable. So now what we want to do is consider x as a random variable, which is epsilon I times xi. This is our random variable. Then what do we know? We can do two things. One, we show that this is quite concentrated. This must be quite concentrated. And then we show that this cannot be concentrated. You might be wondering what am I showing, what am I saying, but there are two different, you have to quantify the concentration. You can show that the how well concentrated it can be lower bounded and upper bounded, and then that gives you something. So roughly why it must be concentrated is that you can actually measure the variance and show that this must be somewhat concentrated. And then why it cannot be too concentrated is that for different choices of epsilon 1 to epsilon k, you get some value of x. But for two distinct choices, epsilon prime k, epsilon prime 1, for these two choices, this value cannot be same. Because we assume that this is a set having distinct sums. So for different choices of these two, the value of here cannot be same. So even if you prove some expectation, the value of x cannot be concentrated on the same point twice. So it occupies, this each value at most once. That means it should somehow spread out. Because this is one of, so there are 2 to the k many possible sequence of 0, 1. And it's never like two different tuples give you the same value. So that means that if you have expectation here, and then this is the value, say some integer value, I minus 1, I minus 2, and so on, the probability that x has value I is at most 1 over 2k. And here is at most also 1 over 2k, and at most 1 over 2k here. And then it's either 1 over 2k or 0. And the summation of probability must be 1. That means, but each point the probability is bounded. That means it must be very, spread out. So it gives that it cannot be too concentrated. But we use the second moment method to show that it is somehow concentrated. That gives us the inequality. So let's first measure how spread out it is, the variance of this. Obviously, the expectation is easy to compute because it's indicates a random variable having values 1 or 0. So it's half of the summation of xi is the expectation, and its variance is, so for each xi is each epsilon I is either 1 or 0 with probability half and half. For that, variance of this xi is 1 over 4. So variance of then epsilon I xi is nothing but 1 over 4 times xi square. So you get this. And each xi has size at most n, so this is at most n squared k over 4. Then, by applying Chebyshev, for any lambda bigger than 1, what we have? The probability that the x is too concentrated around its expectation by lambda n square root of k over 2. So take the square root of this is at least 1 over lambda square. So here we flip this 2 inequality here. So it's essentially, it's the same inequality with Chebyshev, but usually you write this way and then this way without this 0. But it's the same thing. You can easily show that this is same. So you have this concentration. But as I mentioned before, however, as this set have distinct sums, for any value t, the probability that x equal t is either 0 or 1 over 2 to the k. So that means this lower bound is actually we can take a upper bound. So you have mu here, and then you deviate by the mu plus lambda n square root of k over 2, mu minus lambda n square root of k over 2. So how many integer values are here in this range is at most, lambda n square root of k plus 1. And then each one of them has a probability 2 to the minus k at most. So this is an upper bound. So now we have this inequality. You just, you have this one term n, so you solve it, and n is at least 2 to the k times 1 over 1 minus 1 over lambda square, say minus 1 over square root of k lambda. And you just put some lambda bigger than 1, say bigger than 1 and between 1 and some number. Then you can actually show that this k is at most log n plus half times log n plus some constant. And by taking the optimal one, this shows that this Fn is also upper bounded. And we will check some more examples, some more application of the second Momo method. One of them is about the random graph. So probably in this video, let me define several concepts about the random graph model, and then we actually prove our result in the next lecture. We say that the binomial random graph model GNP, it's also called the Eredish-Renyi random graph model. This is a probability space over the set of graphs, and the graphs are the vertex set, bracket n. So 1, 2 to n, the integers are vertices, and this is determined by the probability that the ij is an edge in the graph G. So G is a graph that we obtain from this probability space. This is P. So I and J forms an edge with probability P, and these events are all independent, mutually independent. So what I mean is that for every pair ij, you flip a coin, which comes up with head with probability p, and then tails with probability 1 minus p. If it is head, you add an edge. If it's not, you don't add an edge. And then all those events are independent. Then you get a graph. So this actually gives us that, let's say, Gn half consists of the graph, which is, say, 1, 2, 3. This A graph, and then this has probability 1 over 8, this has 1 over 8, 1 over 8, 1 over 8. So this is Gn half, probability space Gn half. And say G2 third is that the same graph, but the probability here is that 27 over 8, 27 over 4, 4 over 27, 2 over 27, 2 over 27, 2 over 27, 1 over 27. So each graph now appears with a different probability. And here, what it means by mutually independent is that, so if you have ij, let's say some pair ij, and I prime, j prime, and I double prime, j double prime, which is not, so let's say these three are different. And these two events, this event is independent from this event, and this event is independent from this event. But the mutual independent means that this is independent from any combination of these events. It is independent. So for example, if you have a probability space here with this is A, event A, this is B, this is event C. And let's say probability, here is 1/4, the probability distributions are here, so that the probability of happening A is half, probability of B is also half, and probability of C is also half. A and B are independent because even if you assume B happen, probability of A happen is still same. Probability of C and A are also independent because A still happens. A is independent from B and C. But probability that let's write slightly differently. So this is A. Give me a moment. And this is B. And this is C. But now, so these three things still happen, but when B and C both happens, then probability of A happen is 0. And probability that A happens when B happens but C doesn't happen, then this is 1. Because what's this event? This event is this. In here, A never happened. And this event is here. Here, A always happened. So which is different from A. So in this case, A is independent from B, A is independent from C, but it is not mutually independent from B and C. So no matter how we write in here in terms of B and C or its complement and event happening together or the union, whatever you do outside here, the probability of A happen is always same with probability A. Then you say that A is mutually independent from a collection of events. So here, this means that whether this edge is here or not is totally independent on whatever happens outside. So that's a random graph model. And in random graph model, we say that if a property P holds for, so we can actually measure the probability of certain thing happen. For example, here, these four graphs are connected and these four graphs are not connected. So you can actually show that this graph is connected with probability half. So see, I'm a bit abusing the notation, abusing the terminology, saying that this is actually a probability space, and this is the resulting graph. But sometimes I'm confusing with these two. I can just say random graph is connected with probability half here, and random graph is connected with probability 20 over 27 here. So we can actually say that this property holds for this random graph. And if such probability we can compute. If the probability is 1 minus liter of 1, so it's converging to 1 as n goes to infinity, where this liter of 1 term tends to 0 as n tends to infinity. Then we say G and P satisfy P with high probability. Or sometimes we said asymptotically, almost surely. And we sometimes write this as just with high probability with WHP or AAS. It's asymptotically almost surely. And in here, if you see, the probability of this being connected was half. But now here is 20 over 27, which is higher value than before. So as P goes up, certain probability of certain thing happens gets higher. So for example, I mean, this connectivity, if let's say before n is just 3, but let's just say n is not fixed number. And as p goes up, if p is 0, then it is almost surely, it is with high probability not connected because there will be no edges. But if p is 1, then you will always get a complete graph. So it is connected. So the probability goes up between 0 and 1. So at certain point, there are certain points that the probability becomes bigger than half. Then we are interested in what P makes it that it is more likely to be connected than disconnected. And of course, determining exact P, making the probability half is difficult. So we are interested in this. So a function fn is a, say, threshold function for some graph property P if the following holds. If whenever P, which is a function of n, satisfies this Pn over, let's write R threshold. This is, something which is much smaller than Rn, which goes to 0 as n goes to infinity. Then the probability that this GNP satisfies P tends to 0. And whenever Pn over Rn goes to infinity, then the probability that GNP does not it satisfies P tends to 1. Then we say this is a threshold function for the property P. So as I mentioned before, so when P is 0 and 1, the probability that G and P is, say, connected is 0 here, 1 here. So our intuition says that at some point it should be above half. But finding this exact point is difficult. So we want to show that if this somehow shows in this way, so it is almost, close to 0, and then at a certain point it spikes up to 1. Then if this happens, then it has a threshold around this. So many studies about this random graph model is that whether this satisfies certain property with, high probability or not. And also determining that for, which value of P does it satisfy certain property with high probability, certain property with high probability. So next time what we'll do is that if you think Gn0 and Gn1, then this is empty graph and this is complete graph. So this contains every H as a subgraph. And this contains essentially no H as a subgraph, as long as H is not empty. So for fixed H, and if you increase this P from 0 to n, at some point, H appears. And what's the threshold function for having H as a subgraph? So that's what we will do next time. I mean, to show that we need to find the Rn such that if Pn is much smaller than Rn, then you don't see any subgraph H. But if P is much bigger than Rn, then with probability 1, you always see one copy of H in GMP. That's what we want to show. And for showing that, we use the second moment method. So that's what we will do next time.